All right, hello everyone, and welcome to our third video for Unit 9. Today we're going to be covering 9.4 and 9.5, which covers thermodynamic and kinetic control, as well as free energy and equilibrium. So first we're going to talk about why some reactions are thermodynamically favored, but occur very slowly due to high activation energy barriers. When this happens, the reaction is what we call under kinetic control, meaning rate is going to determine whether it proceeds and not favorability. A reaction not occurring quickly does not mean it isn't favored. It simply means it cannot overcome that barrier easily. So thermodynamic favorability, which we now know can be denoted by negative delta G, tells us whether a process can occur. And kinetics, which we learned a lot about in Unit 5, tells us how fast it occurs. Now, if a reaction is thermodynamically favored and it does not proceed at an observable rate, it doesn't mean that it's not thermodynamically favored. It could just mean that that activation energy is so high that the collisions that actually have that minimum amount of energy are few and far between. So the actual process takes a really long time that if you were trying to measure that rate, it would be nearly impossible to define. All right, so let's look at one of these types of reactions. Let's say we took a diamond and we put it at room temperature and pressure and we let it sit for 1 billion years. In 1 billion years, some of that diamond would turn into graphite. Now, we know 1 billion years is an incredibly long time, such a long time that we can't actually see this change from diamond to graphite. However, if we look at the standard Gibbs free energies of formation for diamond and graphite, and we solved for the overall change in Gibbs free energy, you would see we get a negative delta G value, which means it is thermodynamically favored. However, because the activation energy is so high to go from diamond to graphite, very little particles actually meet that barrier of activation energy to form into graphite. This means that diamond is kinetically stable and does not spontaneously convert to graphite under normal conditions, even though the process is energetically favorable. A 0.2 mole sample of H2S and a 0.1 mole sample of SO2 are placed in a previously evacuated 10-liter vessel at 298 Kelvin. Even though the reaction represented by the equation above is thermodynamically favorable, the formation of S was not observed. Which of the following best explains why S is not produced at 298 Kelvin? So looking at this equation, it's saying that we have a delta G of less than 0, which means we know it is technically thermodynamically stable. However, it's observed that none of the sulfur was forming. So what can be a reason for that? And we just talked about if something has kinetic control, it means it can still technically be thermodynamically favored, but if that activation energy is far too high, most of the molecular collisions are not going to produce a product, which is why even though we have thermodynamic favorability, not a lot of those product molecules are actually going to form. So the answer would be C. At 298 Kelvin, the energy of most molecular collisions is lower than the activation energy for the reaction, which means those products are not going to form at an observable rate. All right, this next practice question says the combustion of ethanol is represented by the equation above, and the standard entropy and enthalpy changes for the reaction are provided. When the reactants are combined at 25 degrees Celsius, essentially no carbon dioxide or water is produced after a few hours. Which of the following above can best explain the low yield of the reaction under these conditions? So, thinking about kinetic control, if this reaction is thermodynamically favored, but our products are not forming, then we need to think why in this scenario would our reactant molecules not be forming into product molecules? And that again is going to go back into our activation energy. So in diagram 2, you can see we have a much larger activation energy barrier than we do in diagram 1, meaning that few molecules have enough energy to successfully react at that temperature and form products. And because of that high activation energy, the reaction is going to occur very slowly, so little product is going to form even though the reaction is favorable. All right, and then moving on to 9.5, which is on free energy and equilibrium, we're going to talk about how Gibbs free energy is connected to equilibrium. So if delta G is less than 0 or negative, we know that the reaction is thermodynamically favored and products are going to be favored at equilibrium. So K is going to be greater than 1. If delta G is greater than 0, meaning it's a positive delta G, then we know that the reactants are favored, so K is going to be less than 1. And when delta G is close to 0, the system is going to be near equilibrium where our rates are equal, and that is going to give us a K around 1. All right, so what I would like you to do is pause this video, and I'd like you to think about what you know about Gibbs free energy and what you know about the equilibrium constant. And using those two values, how could you relate them to each other? So delta G is going to tell us the direction of favorability, meaning if I have a negative delta G, I know that I have a thermodynamically favored reaction or a spontaneous reaction, and I know it's going to form products. So I know if I have a positive delta G, it means I am not favorable, which means I'm going to be lying in terms of equilibrium on the reactant side of things. I'm not going to be forming products because I'm not spontaneous. So with a positive delta G, that means I'm going to have a K that is less than 1. Now with a negative delta G, when we have that spontaneity and we have that thermodynamic favorability, we're going to want to make products, which means our K is going to be greater than 1. All right, so I'm bringing back this information from Unit 7 because I think it's easier to visualize this way. But if you think of being in the middle of your chemical equation, at this point you have equal amounts of your reactants and your products. That is when your K value is equal to 1. Now, if you were to move towards the product side and increase your number of products, that means you are going to have a higher K value than 1. And same going in the other direction, if you are to increase your amount of reactants, now your K is going to be less than 1. It's the same concept with Gibbs free energy. If we have a Gibbs free energy of 0, that means we are right in the middle. We have both sides working at the same rate, so we kind of have forward reaction and reverse reaction being equal, meaning it's not spontaneous going forward, and it's also not spontaneous going reverse. So delta G being 0, I like to think of the same as K being equal to 1. And then when I have a negative delta G, I know that spontaneity means my reactants are going to be turning into products. So because I have more products, when I have a negative delta G, I know my K value is going to be greater than 1. And then in opposition to that, if my G is positive, that means I am non-spontaneous. My reactants are not turning into products. And because I have more reactants, I know my K values are going to be less than 1. So if products are favored in their standard states at equilibrium, delta G is going to be negative and K is going to be greater than 1. If reactants are favored in their standard states at equilibrium, then delta G is going to be positive and K is going to be less than 1. And if neither products nor reactants are favored in their standard states at equilibrium, then your delta G is going to be equal to 0 and your K is going to be equal to 1. And we can relate all of this to an equation given to you in your formula sheet, which is here. And that is delta G is going to be equal to negative RT times the ln of K. And R is going to be your gas constant. We're going to be using 8.314 because that's one with joules in it. Temperature is going to be in Kelvin, and then ln, or the natural log of K, is your equilibrium constant. So we can directly connect delta G to our equilibrium constant using this equation. So just remember, if K is greater than 1, then delta G is going to be negative. If K is less than 1, delta G is going to be positive. And if K is equal to 1, then delta G is going to be equal to 0. So let's relate that to some practice problems. The graphs above represent the changes in concentration over time for the reactant and product of two separate reactions at 25 degrees Celsius. Based on these graphs, which of the following best supports the claim that reaction 1 is thermodynamically favorable, but reaction 2 is not? So we are relating concentration of reactants and products to thermodynamic favorability, which means I'm relating delta G to K, or my equilibrium constant. Now it's saying that reaction 1 is thermodynamically favorable. And I know if I have something that is thermodynamically favorable or a negative delta G, I know my K is going to be greater than 1. And a K that is greater than 1 means I have more products than I do reactants. And in reaction 1, we can see that at equilibrium, I have a lot more products than I do reactants. And that is why reaction 1 is showing a thermodynamically favorable reaction. All right, and this one says the synthesis of ammonia is represented by the equation above. Based on the equilibrium constant K and delta H given above, which of the following can best be used to justify that the reaction is thermodynamically favorable at 298 Kelvin and constant pressure? So let's first start with our K value. We can see that we have a K value of 5.6 times 10 to the negative fifth, which means I am definitely product heavy. And when I'm product heavy, I can assume that my reaction is going to be thermodynamically favorable. And when I calculate delta G, I know I'm going to get a value of less than 0, because if I'm making a lot of products and on top of that I have a exothermic reaction, all signs are pointing to a spontaneous or thermodynamically favorable reaction. And that means I'm going to have a negative delta G. So both of these have delta G, both of these have K is way greater than 1. So I am looking for the equation that tells me that delta G is going to be negative, which would be